2, 1, go.
All right, I'm Jake.
I'm Noah.
I'm Ryan.
And we are Team Raft, which stands for Radio Assistive Firmware Technology. And it ties into a group of ducks on the water. It's called a raft. And so you'll understand why the duck imagery is very important later. So our client is Project Owl, a Brooklyn-based startup, pretty new. They don't have any clients yet. They won the IBM Call for Code Challenge in 2018. And so that's given them funding. And so currently they're out testing in the field and trying to develop a customer base. So they have two main aspects of their system, the Owl DMS, which is their cloud data management platform, and the DuckLink hardware. So the cloud is where the founders, specifically Brian and Nick, who's been our main point of contact with them, they are very well versed in cloud software. And so they have this data logistics platform that customers can use. And then the DuckLinks are the hardware device they've developed to be able to collect that data. And so that's what we're going to be focusing on. So the DuckLink is a low-cost, rapidly deployable peer-to-peer device that can create a network in an area where there is no wireless network. So their main example is for disaster response. So it's basically a small board inside this casing, and so they can have different configurations. So this one is from their Puerto Rico test, which had it's called the Permaduck, and it has a solar panel on it. And so it's designed to be able to stay there for long periods of time. But so yeah, this is another example of the internals. So they have this development board that they got off Amazon. And so it's a very thrown together device. They really focused on their software, and this device is developed through open source, through like basically Slack and through Slack. And so their task for us is to redesign this because it had some, I'll go into the use cases first. So the use cases, one of the big things is they want this to be able to be used across many applications. So emergency response, they can rapidly deploy these across the city if they need to, using drones or just going around and deploying them. And so this would help people communicate with emergency services to tell where they need help. You can also do compromised locations, and the Department of Defense would be interested in putting these in warehouses because they have large warehouses and they routinely lose thousands of dollars of equipment in these massive multi-football sized warehouses. And so you could place these on them and they can track their locations with it. And then also another fun one that they've designed is a disco duck, which would be for like music festivals or other events that the network is crowded. So you basically create your own little mini network with your friends, and you can carry them around and like on a backpack or something and communicate easily with that. So the issues are,
So we're going to talk about hardware and some of the issues with the current configuration. This is the current setup, like Jake said. This current health tech board is off of Amazon. It's $20, $25 per device. And then they zip tie it together with this big battery. You can tell the real difference in the size here. So one of our main goals is going to be to increase the power optimization so we can decrease the size of that battery and get a smaller package overall. During testing, we found out these boards are actually pretty low quality. And even if they said they would be outputting data, 10% of them actually would be doing nothing at all. So it's really hard to find that if you're not in a testing environment. And one of our goals is to increase the general quality of these boards. Another thing is unnecessary components. Like you saw before, there was an LED screen on top, which was hardly ever in use. So by removing those unnecessary components, we can hit on the next 2 points, which is power optimization and lowering the price point. These are the two main goals of our project, really. Project Owl is a startup. They don't have infinite money. We need to make sure that these devices are scalable. They're going to have their own factory printing these out, and we want to make it affordable for them. And then also the current modules don't have GPS at all. So we'll be adding a GPS antenna, and that will help with some of the use cases like asset tracking in those warehouses. And then,
yeah, as you mentioned, the goal is for us to make a bare bones, totally slimmed down, single-use board for them to use. Main features. This is kind of a general system over hardware level block diagram, stripped from the lower board that we're kind of basing it off of. Main features: charge controller and the battery. Currently, they're using kind of a plug-and-play USB battery, which we want to avoid. Have all that consolidated onto the board. GPS and LoRa. He mentioned the battery thing or the antenna thing. Turns out we found an antenna where GPS and the Wi-Fi and Bluetooth can actually share one antenna. So that's pretty neat. Other main features: it's all going to be powered by USB, USB to UART bridge to talk to the MCU, all debugging controls, power, battery. Flash memory and EEPROM, we're thinking we might have some data logging on it. Other than that, mostly we need some external storage for over-the-air updates and stuff like that. A key feature that they wanted is the expansion ports. They were saying for the monitoring, like air quality monitoring, you're going to need some sort of sensor for that. But in other scenarios, you may not want a sensor at all or completely different sensor. In that case, as many interface options as possible is what we're going to want. This is kind of an overview of the communication systems. As you can see, there's a lot of similarities. Semtech chips, ESP. This is Semtech. I think they have a patent on LoRa or something, so it's pretty much the only one you can get. Industry standard. We decided to remain with the ESP32 because it has a lot of features, mostly the integrated Wi-Fi and Bluetooth. It not only condenses the size on the chip, but it also slims the cost down and makes it easier for us to work with. The two major differences is the addition of a GPS sensor, external antenna connectors, and then, the swapping of the coil antenna to kind of the fancy dual band antenna. I should mention that. The external connectors is a big thing because the internal antenna it's a really low gain, low range, and the higher gain antenna you have, the longer range, obviously. So with the external connectors, you can attach a much larger antenna, usually get much better range. But when you either don't need that range or simply don't want it, you can switch to an internal antenna and still have the same basic functionality. All right, here's a couple of design matrices. This one's for the antenna that we came up with. The antenna is pretty neat, as it's basically a tiny little ceramic antenna that just has 2 feed points. And since Bluetooth and Wi-Fi both run off 2.4 gigahertz, that'll be one, and then the 1.5 for the GPS is going to be in the other. This is a preliminary LoRa PCB layout. Semtech LoRa chip, the whole impedance matching circuits and all that. We were debating whether or not to use what sort of output powers to use. We're trying to figure out the proper balance between output power or power draw and then range. So you can either do the boost or just regular. We're going to run some tests on that to figure that out. But yeah.
So with the current hardware, like he said earlier, we just have USB power input from that large battery. And we want that as an option, but we'll also be having solar panels that can charge our device. We want to have 2 main voltage rails. I'm sure a lot of you know the standards. We'll have a 5-volt rail and then a 3.3 volt rail. So we'll need some voltage regulators for that. Our integrated battery charge controller, we had to decide between a normal PWM solar charge controller or a MPPT, which is maximum power point tracking. And for solar devices, it's much more efficient than the PWM with some trade-offs in cost, size, and complexity. But with our design matrix here, we decided that MPPT would most likely be better overall for our device. And then the other design matrix up top is for a soft switch or a hard latch. Basically, that would be a switch that turns on the device. Is it a mechanical lever or a button that stays down when you press it, or the soft switch, which was suggested, and that would be a normal button that pops back up after you press it, but if you hold it down, it might power on the device, and then you can hold it down again to turn it off. That saves cost, size, and it's just a little bit more complex to integrate. And then the next steps for the hardware side of this project is to solidify circuit components and the design. These circuit components specifically would be stuff like specific values for resistors and decoupling capacitors. And then we'll be designing the PCB schematic and layout and sending that off to get manufactured. Keeping in mind RF, noise, and interference, because it plays a large part in your PCB design when you have RF. And then most likely our first version of this device will not work right away. So we've allotted time for testing and revisions.
So I'm going to talk a little bit about the firmware that Project L is currently using on their boards and how we are going to try to improve upon their software firmware. They're currently running an Arduino-based code base for their ductlink devices, which is really good for at-home DIY developers because it allows you to select between any of their like device frameworks. So there are three. There's the ductlink, the mama duck, and the papa duck, and each of them serves a different purpose in their framework as a whole. And so in order to choose between those and set up an entire network, all you have to do is change one pound define, and then it allows you to set up the device for whatever purpose you need it for. So this is a really portable and easy to use implementation currently, but we want to try to improve upon it because their software can only run on these boards that you have to buy from Amazon. And so we're going to have to develop a new software base if we want to use it on our own board. A couple of issues with their current setup right now is that they use a pretty inefficient broadcasting protocol. And by that we mean currently all of their boards always broadcast their data, and whoever receives it tries to route it by just broadcasting it again, which is not particularly efficient. And we want to implement some sort of dynamic routing protocol where we can send information to specific boards along a route and just have it a little bit more efficient and try to limit network traffic. And then one of the big things we mentioned before was that we want to limit power consumption on all of these boards. That's one of the main goals of the project. And we think one of the biggest like avenues to do this is going to be through our firmware, because even though Arduino has a lot of options for using like low power modes and stuff like that, Project L currently doesn't use any of them. They have a pretty bare bones framework for just doing all of their network communications. So that's going to be one of the main goals of software, is to implement low power modes and see how we can do that. And then another big thing is that since they're using the Arduino IDE for all of their software development, Arduino uses a single-threaded kind of execution style where it doesn't have any option for running multiple tasks at the same time, which means it is 65% slower than real-time operating systems. So we're going to try to move to an operating system that'll allow us to run multiple tasks at the same time to handle all of our networking communications. And then another big thing is that they want this to be a mesh network device, which means each device needs to be sending and receiving data in order to route information the most efficiently between all the nodes in the network. And currently, their software doesn't do this. Their ductlink devices, which are what you connect through Wi-Fi in order to transmit data to, like off of your phone, only broadcasts information and doesn't actually receive anything. So that means the way it's set up right now isn't a true mesh network. And so one of their goals is to try to make a more efficient protocol for doing this. And so, as I mentioned before, we're going to try to move off of the Arduino development framework and go to Espressif's framework, which is called the Espressif IDF, which just gives you a whole set of libraries that allow you to program the ESP32 chips. And it just makes it a lot easier to interface with all the networking modules on the device itself. And as a part of this, Espressif has implemented FreeRTOS within their framework. So they have an operating system already running off the shelf when you use their software development kits. And so we think this will improve our manufacturing speed for the board because they implement a lot of libraries that we don't have to port over ourselves. And then here's our design matrix for deciding between Arduino and the ESP IDF. So obviously, I mentioned before that the ESP IDF will allow us to run 65% more efficiently than using their Arduino. And it comes in front in libraries because we don't have to go through a bunch of external manufacturers and companies to try and find like libraries to deal with different things on our board. The Espressif IDF allows us to do a lot of these all in one place. The only thing that we were considering Arduino for is its usability, because obviously it's pretty ubiquitous in at-home DIY projects. It's a pretty easy to use software. So that's the only really benefit it had, but we ended up deciding that using Espressif's framework was better in the end. And then just for our next steps in firmware, which we're going to start developing soon, obviously the biggest goal is to port everything from the Arduino code that it's in right now to C using Espressif's software development kits. And then past this, we're going to try to improve upon the mesh network protocol that they're using in two main ways. We want to implement a message confirmation system, because currently if you're using the SOS services on the duck link, you don't get any confirmation telling you that the mama duck received these SOS calls, which is a pretty big problem if you think your call for help got received and it actually didn't. So that's going to be one of our big changes. And then, as I mentioned before, we're going to try to add a dynamic routing protocol to make it more efficient. And then I also mentioned that we're going to try to use power saving modes on our board once we have it developed to limit power consumption. We're open to questions.
Any questions?
What's the current range for electric communications?
Currently with the antennas we got, not very much. The theoretical range of Wi-Fi is at most like 100 meters. Yeah. And the LoRa should be about 10 or so. We haven't actually tested if it can actually go 10. With the higher gain antenna, we're hoping we can at least hit that.
So you connect to the duck link through your phone with Wi-Fi, and then they communicate with LoRa.
So you mentioned the ducklings not currently being able to receive data, they're just transmitted data.
Yeah.
So how does the network work currently?
Well, so the ducklings are the devices that that get deployed like all around, and then you'll have one mama duck that all of these ducklings kind of communicate with. And so in order to send information into the network, you connect to the ducklink through Wi-Fi, and then it receives information through Wi-Fi, and then it'll broadcast that through our LoRa network communications, but it won't receive anything through LoRa, so it can't communicate with any of the other ducklink ports. It can only communicate with like a phone or like a laptop.
So it's not really much of a mesh network right now. There's a few mama ducks that act as the mesh, but between all the duck links, they don't, and this makes it hard to set it up because you have to have a mama duck that's in range of a certain amount of duck links, but also in range of another mama duck, and it's all the same hardware. It's just different firmware talking to it. So we want to have a dynamic one that would set up, like turn one into a mama duck when it's in the right position instead of them having to figure out. Especially because one of their deployment strategies is just floating it on water, which they just did in Atlanta at this like big government test facility. So that would be hard to decide which one's the mama duck if they're floating around.
Yeah, the basic hierarchy right now is you have all these ducklinks, and then you have those talking to a mama duck, and the mama ducks can talk to each other, and a papa duck that sends the data to the OWL data management system that's actually connected to the internet.
The mama ducks, they didn't have different types of energy capabilities though, or they did?
No, currently they don't have any like power optimization software implemented on it.
What, like a solar panel, or was that a pump duct?
So that's not necessarily like any specific kind of duct. That's just one of their products. Usually you can hook the devices up to USB and charge it through that. But when they were deploying it in Puerto Rico, obviously they didn't want to have to keep going and replacing batteries on it. So they instead just hooked it up to a charger that would charge through solar power.
One of the things we want to focus on with this project is making it as versatile of a product as possible, because I want to use one board for the different types of ducts and as well for different applications. So that's why we have things like the GPIOs and the extra antenna ports to be able to decide later, essentially, how the board is being used.
Cool, thanks.
Yeah. Paul's going to do a quick demo of how the device works currently.
So yeah, this is the current